this video will help you increase your confidence in answering problems of alkene reactions on maybe a quiz or an exam you have or a homework problem you have coming up. If you're not quite ready for practice problems, there's a video linked in the description which will explain alkene reactions, and then once you go through that video you can come back to this one, and this will kind of give you some practice with some of the problems that you might see going forward. This is important. So reactions, organic chemistry reactions are important because this allows molecules to change from one form to another form, as you'll see here with these problem sets. So let's get into it. Here's the first problem. Go ahead and give it a whirl and then pause the video, and then when you think you're ready and have the answer, come on back and I'll walk through the answer with you. So in these practice problem videos, I don't just give you the answer, I kind of walk through how I got to the answer, because then that may help you make sure that you're following the processes of these problems in an effective way for you going forward. So the first thing I'm going to do, I'm going to change the color of this H2 to put it like that. That's H2. I changed it to red so we see when we do the reaction, you'll see where those two hydrogens went. One thing to remember really in a lot of alkene reactions, I don't want to say all, but in a lot of alkene reactions, what's happening is it's that double bond that's going to get attacked. We're going to break that double bond. That double bond is very reactive, so we're going to break that double bond and add hydrogens across, or add the molecule, a molecule across that double bond, so to speak. And so I'm going to write this molecule out in a little bit different way. What I'm going to do here is kind of rewrite it, but let's write it in a way, whoops, I don't want to do that. And I'm going to rewrite it in a slightly different way just so we can see what's happening. So I'm going to move those hydrogens away a little bit. Don't like that. So I'm going to move those hydrogens connected to the carbons of the double bond just off a little bit. And then what's going to happen here is when we have alkene reactions, not only are we breaking the double bond, it's typically through an addition reaction, i.e. the two molecules involved in the reaction are going to be added together to form a single product. So notice we have this alkene plus this hydrogen, and what's going to form is a single molecule. And what happens is those hydrogens will actually connect to the carbons of the double bond. So this bond will get moved over to here, and this bond will essentially get moved over here. Now this is not exactly how it would work mechanistically, but the product is going to be correct. And so when I move those two bonds in that way, and I erase all the bonds that were broken and then added, we can see it ends up in a molecule like this. And so with this reaction, we ended up with an alkane, and realized we started with an alkene. So in this reaction, we actually change an alkene molecule into an alkane molecule. Notice everything is happy here. All the hydrogens have one bond, and all the carbons have four bonds to them. And so all that molecule is very satisfied with that arrangement of atoms. This type of reaction is called a hydrogenation reaction because we're adding H2 to the alkene molecule. Also, I failed to mention that a lot of times these reactions also have catalysts that help the reaction go forward. Hydrogenation reactions a lot of times will use palladium, and so you'll see that around the arrow, the reaction arrow showing PD or something. It's not a reactant, it's not a product, it's just the catalyst that helps the reaction go smoothly forward, but it won't form one of the products. So give this second reaction a try, and so each of the problems we have going forward will kind of put a new wrinkle in that you can learn about as we kind of solidify our understanding of alkene reactions. So pause the video and then come on back and we'll chat about it. So once again, I'm just going to change this to red. And again, what happens is that bromines, and this is a halogenation reaction because that's bromine's a halogen, the bromine will attack that carbon-carbon double bond. It doesn't matter that one of the carbons is in a ring structure as we see here, it's still going to do the same thing. And so if we bring that over, we'll see that bromine, one of the bonds will move here to form between the carbon and bromine, and the other bond will form between the carbon and the bromine. And so when we do that, we'll get a structure. I'm going to move those bonds, and we'll see what we get in the end. So notice in this reaction, the double bond is broken, and we added the bromines to each of the carbons of the double bond, and so we get that structure there. If I were to draw this a little bit nicer, it's a little bit hard to, got really jammed up there with a lot of atoms and bonds, but essentially it looks like this. We got a CH2 with a bromine attached to it, and then the other molecule attached on is the other bromine. Notice the double bond used to be right where the arrow is going to be pointing, that where the double bond used to be. We broke that double bond and added bromines to each of the carbons attached to that double bond. Again, I'm not showing too much of the correct arrow pushing or the movement of electrons too detailed. It's just more what is the product of it, not so much what is the mechanism of the reaction. Now let's step up our game a little bit. Let's go ahead and do this reaction, a hydration reaction, because we're adding a molecule of water, and water sounds like something that would hydrate you, and so this is called a hydration reaction. Go ahead and see if you can get the product or products of this reaction, and then we'll talk about the proper answer to this one. Once again, I'm going to go ahead and put the water that we're adding on in red. And when this adds on, it'll actually add on a hydrogen to one of the carbons and a hydroxyl group, the OH, to the other carbon. And again, anytime you see this alkene, that double bond, that's what it's going to go after. That's what it's going to break. And so I know that when I do that, I'm going to go ahead and put the H here and the OH here. And we're going to go ahead and, again, just to show you kind of where the electrons are going a little bit, the electrons will move. It'll break that double bond, so that's the movement of the bonds. And so when we do that movement, let's see what we get. And you can see by hydrating the alkene, we get an alcohol. So earlier when we did a hydrogenation reaction, we converted an alkene into an alkane. With a hydration reaction, we converted the alkene into an alcohol, as we see here, because we can see that OH group sitting on that carbon. Now, if we went ahead and named this guy, what would we get for its name? So first of all, we're going to go ahead and number the carbons, because we're going to be naming it as an alcohol, because there's an OH group on there. The alcohol gets the lowest number possible, so that's carbon 1, carbon 2, and carbon 3. And so 3 carbons long, it's an alcohol, so it's going to end in OL. It's 3 carbons long, so it's propanol. Where is the alcohol? It's on the 1 carbon. And then we have a substituent way up here. That methyl group is on the 2 carbons, so this would be 2-methyl. Whoops, I'm running out of space. Dash 1. I can't get that dash in there. Dash 1 propanol. Okay, great. But wait a minute. Couldn't the OH have fallen on this? If we flip the H and OH, isn't that possible? Well, let's take a look at this. It seems possible that this could have happened, that the water molecule could have aligned next to that carbon-carbon double bond. 1 bond went there and 1 bond went there, just as we did before. And it seems like in theory it could have attached like that, where the OH attached to the second carbon and the hydrogen attached to the first carbon. Now, this wasn't a problem before, because in the first 2 examples we had 2 bromines or 2 hydrogens, so it didn't matter which one went to which. It made the same thing both times. But let's look at this. Let's go ahead and name this molecule, make sure it's different. There's carbon 1, carbon 2, and carbon 3. We know it's an alcohol, so it ends in OL. It's 3 carbons long, so it's propanol. And the alcohol group this time is on the 2nd carbon. And then we have the substituent on the 2nd carbon as well, so it's 2-methyl, 2-propanol. So there's actually, it seems like there is 2 possible products. And that's true, there is 2 possible products, but are they both equivalent into how often they would occur? For that, we'd have to talk about the Markovnikov rule. Now, if you haven't heard of that before, and it hasn't been in any of your classes or anything, or you're not interested in it, this probably suffices for you. You probably are good here. You can go on and fast forward to the fourth example. But if you've heard of the Markovnikov rule, then you might need to hang on just a moment, because the Markovnikov rule says which one is more likely to occur. And so for that one, it turns out that the hydrogen, when you add the hydrogen on, so I'll change my color here a little bit, this hydrogen is going to add, and this hydrogen, we're looking at those two hydrogens, that hydrogen is going to more likely add to the carbon that has more hydrogens on it. That'll be the more likely scenario. So in the left example, the hydrogen added to a carbon that was attached to two methyl groups. So it was attached, in this example on the left, that hydrogen's attaching to a carbon that's not attached to any hydrogens. The right example, the hydrogen's attaching to a carbon attached to two other hydrogens. Therefore, this one, the one on the right, is the one that's more likely to occur, and it follows the Markovnikov rule. And so this one, if you were to run this reaction, this is the product you're going to most likely see. And this one on the right, not so much. Now, depending on the molecule, depends on what the percentage breakdown is, but it could be something like 99% would be in this form and 1% would be in this form, or 95% and 5%. I mean, it's a huge difference between which one is going to form. So if they're asking for all the possible products, both are correct. If they're asking for the one that's most likely to be formed, or the one that's most commonly formed, in this case, it's the 2-methyl-2-propanol, because it follows the Markovnikov rule. If you're not so sure about the Markovnikov rule and want to go through a little bit more in detail, there'll be a video posted that I'll link in the description below. Then you can go kind of rewatch that video to make sure you fully understand that rule. In the next example, I'll show you another application of that rule, as well as learning about alkene reactions. Let's go ahead and give this one a try. This one's called a hydrohalogenation reaction, because you're adding in a hydro, the H, and a halogen, so hydrohalogenation. A little bit different than a halogenation reaction, which would be two halogens connected together. In this case, it's not a halogenation reaction, it's a hydrohalogenation reaction. So once again, I'm going to go ahead and change this into a different color so we can see the actual atoms being added to the alkene. We see we have an alkene. Again, most commonly with these alkenes, you're going to be breaking that double bond to a single bond, and you are going to be adding something to those two carbons that were part of that double bond. And so in this case, we can see what we're going to be adding. We're going to add in an H and a Cl, and those electrons will move, essentially moving those bonds as the arrows show. And when we move those bonds, we get a structure like that, and so that's a possible product. And we can go ahead and name this product. And so I'll go ahead and number the carbons. 1, 2, 3, 4, 5. 5 carbon chain. And so that is a pentane. Ane because they're all single bonded. Pent because there's 5. And then there's a chlorine on the 2 carbons. So this is 2 chloropentane. Now, is that the only product that is possible? I think you guys are getting wise. There might be another one here, so let's take a look at that. So it is possible that the hydrogen and chlorine attached to the other carbon, and flipped it from what we just previously did. So that's what I'm showing here, where the double bond, not the double bond, but the bonds from between the hydrogen and chlorine will move, or the electrons will, and then the electrons from the double bond will also move, so we'll move those 2 bonds as shown there. So now that we have the 2 names done, we have 2-chloropentane and 3-chloropentane. If you're just looking to find out what are the possible products, not both of these are products, or possible products. If you want to know which one's more likely to occur, i.e. you're going to use the Markovnikov rule, then we have to investigate this just a little bit farther to figure out if 2-chloropentane or 3-chloropentane is the more common product. So remember, the Markovnikov rule has us look at the carbon the hydrogen attaches to, the hydrogen from the hydrogen chloride hydrohalogen molecule, the reactant, and we can see that the hydrogen, shown in red, when it attaches to carbon 3 in the structure on the left, there is one hydrogen attached to carbon 3 of that structure. The other group attached to carbon 3 is an ethyl group. That's not a hydrogen, and so that one doesn't count. So carbon 3 is attached to one hydrogen. Carbon 2, where the other way the hydrogen could attach to this structure, shown in red, carbon 2 is attached to a methyl group. That's not a hydrogen, and it's attached to a hydrogen. That is a hydrogen. And so carbon 2 is attached to one hydrogen. Carbon 3, the structure on the left, is attached to one hydrogen. Therefore, the hydrogen in hydrogen chloride equally attaches to both just as easy. And so what that means is neither structure is preferred over the other. And so if you look at the products of this reaction, about 50% will be in the 3-chloropentane form, and you could estimate that 50% would be in the 2-chloropentane form. The Markovnikov rule states that if the carbons the hydrogen has the potential to attach to, in this case carbon 2 or carbon 3, if both carbon 2 and 3 have the same number of hydrogens, the products are equally represented in the products. Now it could be 45%, 55%, because there could be some other reasons why it might prefer one over the other. But Markovnikov rule just kind of says if one's heavily preferred or if they're kind of equally preferred. And so in this case, both are possible, and actually both are going to be right around 50% of the product. So if you made this reaction, if you did this reaction in a beaker, you'd get both. If you want to see some practice problems with other families like alkynes, which will probably be the next one you'd want to learn a little bit about, I've linked those in the description of the video. Hopefully you feel more comfortable dealing with reactions with alkenes.